So just to remember, what we already said is, in order to carry this out efficiently, quantumly, what we do is put the even inputs, classically we put the even inputs here, the even numbered bits here, the odd numbered inputs down here. We do the FFT sub m over 2 on the top and the bottom. And then what we do is the jth output on the top is this jth output from the, you take the sum of the jth output from the top FFT, and you take the jth output from the bottom FFT, multiply by omega to the j, and you add the two up. For the bottom, what you do is you take the difference, but now again you take the jth output from the top, the jth from the bottom, but multiply by omega to the j, and then you subtract. Okay, so we want to carry this out quantumly. So how do we do this? Okay, so first remember what happens in the quantum case. Well, we only, instead of 2 to the little m inputs, we now have only little m inputs. And we want to carry out a quantum Fourier transform. So the first thing to observe is that in separating out these inputs into the even numbered ones and the odd numbered ones, all we need to do is separate them out according to the least significant bit, right? So we want to take everything with least significant bit equal to 0, and we want to apply a quantum Fourier transform to those inputs, and take everything with least significant bit equal to 1 and apply a quantum Fourier transform to those. But remember, all we have to do quantumly in order to make this happen is we just take the least significant bit and leave it out of the circuit. And we apply a quantum Fourier transform to these m-1 qubits. And automatically, this quantum Fourier transform gets applied separately in superposition to everything where the least significant bit is 0, because these cannot interfere with those where the least significant bit is 1. Okay, make sure you understand this fact. So what we are doing is, just by putting the least significant bit aside and applying a quantum Fourier transform to these m-1 bits, that applies the QFT sub 2 to the little m-1, which is QFT sub capital M over 2, to these little m-1 qubits. Right? In superposition, it applies it in parallel to the 0, to the even numbered ones, and separately to the odd numbered ones. Okay, this is fantastic. Okay, this is, because this is the quantum magic coming in. Now, what's the next thing that we want to do? The next thing we want to do is, remember, we want to take the jth output from here and the jth output from there, add it to get get this answer, and subtract to get that answer. So how do we do this quantumly? Well, it turns out in the simplest possible way. All we do is take this least significant bit that we left out, and we apply a Hadamard transform to it. And that does the right thing. It takes, remember what it does? It takes the 0 output, so the amplitude of 0 out here for this qubit is 1 over square root 2 0 plus 1, and for 1 it's 1 over square root 2 0 minus 1. And so what it ends up doing is exactly adding and subtracting the appropriate amplitudes. And for the final thing, what we want to do is we want to apply the appropriate phases, right? So if these wires, if what this number is j, then we want to, and if this qubit happens to be a 1, then we want to apply a phase of omega to the j, right? Okay, so how do you apply, how do you do that? Well, what you do is you now write j as the bits of j. So remember, they are little m minus 1 bits, so let's call them j sub m minus 1, j sub m minus 2, up to j sub 1. Okay, maybe I should have started at 0 to say that that's the least significant bit, j sub m minus 2, minus 3. Okay, so these are the bits of j. So each of these is 0 or 1. Okay, and okay, so what is this? Well, this is exactly omega to the power of, this is the m minus 2th bit, so it's 2 to the, its place value is 2 to the m minus 2. So what you want is, you want to apply omega to the j sub m minus 2 times 2 to the m minus 2. Right? If this is 1, then you want this to be omega to the 2 to the m minus 2. Otherwise, you want it to be omega to the 0 times omega to the j sub m minus 1. M minus 3, 2 to the m minus 3, so on up to omega to the j naught times 2 to the 0. Okay, but you want to, but now you see what this says is you want to apply a conditional phase gate, where if this is a 1, if this happens to be a 1, and if this happens to be a 1, then you apply a phase of omega. Okay, so this should be, maybe I'll write it out here. It should be omega to the 2 to the m minus 2, and so on all the way up through here, where the conditional phase is just omega to the 2 to the 0. So omega to the 2 to the 0 is omega squared. Oh, sorry, omega to the 1. So omega to the 2 to the 0 is just omega to the 1. So you just apply a conditional omega gate, and so on. So you apply, to each of these, you apply the appropriate conditional phase, 2 to the omega to the 2 to the minus 2, 2 to the minus 3, and so on up to just omega. And then you do Hadamard. So now, what does this tell us about the size of this circuit? So what we have is the size of the circuit that we started off with. We had m wires coming in all together. Is the size of the circuit with m minus 1 wires coming in. Plus, how many gates are these? Well, this is big O of m. Right? And if you, what does this recurrence solve to? It solves to S of m equal to big O of m squared. Right? So remember what we are carrying out. We are carrying out the QFT sub capital M, where capital M was 2 to the little m. And so the size of our circuit is little O of m squared, which is little m squared, which is log squared capital M. Right, so it's exponentially better than our classical circuit.